Hello everyone. Yes. Hi Vikas. So in this lecture, what is the most important part here is we need to focus on the three back-to-back lectures of your syllabus where almost like one problem is coming, and these three chapters are very simple, very short, and all the problems are very logical. You don't need to apply a lot of formulas. One is this mechanical properties of solid. Okay, first we need to start with the solid part, that is the solid part. One is with the liquid and one is with the thermal properties of matter, or you can say basically solids. Because after completing these three chapters, you will be very much aware of the properties of solid, liquid and the overall matter in which gases are also present. Then all the problem will become very simple. Okay, extremely simple. Yes, Sai. For sure you can crack this examination. Just focus on your fundamentals. Okay, I'll show you today only. After just listening to this lecture, if you are able to solve each and every JEE problem from the previous year and advance also, mains and advance both problem, then you will be very easily crack this examination. No worries. Okay, so don't worry about it. Okay, so that is basically our target, to crack. So let's start our lecture series in very simplified manner. That what should be, what should, like, okay, sound and everything is correct. Okay, what should be the right method to crack, and what should be the right, yeah, correct. So sound is there. Okay, let's start. So in this chapter, I am dividing this whole chapter into basic fundamental part. What is the basic fundamental? That you can say, like, what we need to do here is, in very simple form, you need to just convert your previous concept of the spring, or you use the force, the area concept, into one single framework. Okay, if you will be able to do that, all the problem will be highly simple. Don't worry about it. Okay, chalo. And the notes of the chapter will be given to you, so don't worry about it. You'll get the notes. Okay, so no need to worry. Pakka, chalo, let's start. So what should be the first thing that we need to study in the mechanical properties of solid? That basically on solid, what type of compressions are there, what kind of, there's a concept of tensile stress, there's a concept of compressive stress are there. Basically why it is actually being created, what was the reason behind that, and how you can treat the same material into the in your, from your previous part, how you can relate basically two materials. So in very simple form, very simple form, can I say, like, if I give you one material, okay, if I give you one simple material, okay, let's suppose if I give you one steel bar, just for assumption I am taking this as like steel bar, you can assume it anything. Okay, just understand, and I am trying to relate these two concepts together so that you will be able to understand that what kind of problem that you can expect in examination. Okay, let's suppose there is a steel bar is there, it is having length L. Okay, obviously it is having some cross section area A, whatever the cross section area is there. No need to get into some disturbances there. Okay, it should not be there, but let's see. Let me check once. Okay, it's not there, like, okay, but there, like, we'll see. Okay, in the starting. Okay, chalo. So what should be your method here? And while you are understanding the concept, you need to understand what kind of bodies are there, like what perfectly rigid body, what do you mean by perfectly rigid body, what do you mean by elastic body, what do you mean by, like, different sort of bodies are there, okay, that we need to understand. But before going into that, we need to understand that there is a lot of problems will be there, like, is rubber is more elastic or steel is more elastic. So there is a concept like what is more elastic, but this concept you can understand only and only when you start understanding this basic fundamental. Okay, let me see. If this is the, you can say, the original length, which I got to know that this L length is there. On that body, if I apply a very small force F, okay, so this is what kind of force? This is an external force, but it is applying in which direction? You can say it is applying in the pulling fashion. It is trying to pull this rod out, but as the rod is fixed, you will get, obviously, for every action there is an equal opposite reaction on the rod. This two forces on the rod, but this force is coming from the wall, okay, this force is coming from the wall in very fundamental fashion, okay, clear? Now let's try to understand what is happening. This is, you can say, kind of you can say the external, or you can say the deforming force. It is trying to deform this body. What happened? What is the basic fundamental that what is actually happening is this body extend its length, but not too much, very less, but yes, it will extend its length. For sure it will extend its length, okay, understood? It will extend its length, but what is the amount by which it is extending its length? That is the most important question that they can ask. But what you need to do is basically, okay, you need to just apply your fundamentals which you studied in the spring part. Okay, you studied something in spring, that is, like, you can say similar part you can apply, okay. But sir, can you tell me, like, from a very fundamental point of view, like, okay, the body is applied by some external force, now the body start moving, okay, the body start moving, but when the body start moving, is there any kind of resistance is there? Is there any kind of resistance there? Yes. What happened when you extend this body by very small amount due to application of this force? Let's suppose this body is moved by delta x, or even you can say the value of x is very small, so you can write only x also. So what is x? X is the displacement, linear displacement for this rod due to the force F. So its original length get disturbed by some value of x. What is happening inside the material? So when I go inside the material, if I take this section, what I saw, that internally this body, this force, whatever the F force is there, it is actually opposed by another internal, or you can say restoring force. But restoring force, or you can say the internal resistance force, is coming what? Internally, not externally. It is coming internally, not externally. That is the most important part. It is coming internally. It is basically a restoring force inside the body which is trying to restore its position. And if the body is in elastic region, which is very important, like after some time, if the body is in elastic region, if you remove this external force, or if you remove this deforming force, when you remove, this body will regain its same length. It will not change its length. So what is x? X is basically at equilibrium position. Okay, this is the equilibrium position. At equilibrium position, what I saw, that due to the application of force F, this body get displaced by some x value, but this body continuously trying to get the same shape of the body by applying the restoring force, but the restoring force is internal force. but the restoring force is internal force. Okay, that's the most important part. So can you tell me what is the difference between restoring force and F? Sir, first thing is, like I am putting in the points. Sir, restoring force is basically the internal resistance of the body. Internal resistance of the body, and that body can be anything. It is not coming externally, it is coming from internal sections. And why it is happening? Because when I pick this material and I saw the internal structure, what I saw is like a proper crystal lattice, means something like this. Please see this part. Something like this. That when you apply any force, the two molecules inside this body, it is having two solid molecule, it is actually attached with each other with some bond. You can present it like a spring, but it is attached with the some bond. And when you trying to stretch this thing by any force F, okay, it will try to regain its position, because just like a spring. So internal structure is almost similar to the spring. So you can assume kind of spring concept, and which is going to be happen, it's sure, for sure. So this material you can assume as like a spring completely, and on that spring, whenever you apply any force on the natural length spring, what happened? The spring will get, yes, spring will get extended by some value or not. When you apply any force F, the spring get disturbed by some value of X or not? Yes, spring get disturbed, but spring create some internal force trying to regain its body, and that is called what? Spring force, which is equal to what? K into X. Mathematically minus Kx, because the spring force should be opposite to whatever the X value is there. So the concept of spring in elastic region or the concept of actual body in elastic region are absolutely similar. Okay. So the second point is, this F is basically your external force. This F is your external force, or you can say the disturbing force. Okay, this is a disturbing force which is trying to disturb the body. And one more important last point is the extension of the body. The extension of the body is in elastic region only. Like whatever we studied in this chapter is only in elastic region, not beyond the elastic region. Bunny, don't worry, just have some patience, because every subject will require some time, to get to that certain point where you can actually start feeling that part. Okay, without that you cannot, like it's not possible. You need to understand, like you cannot understand everything like in one go. It will require some time, and that is what I am doing it. Like I am just keep on, like on the very simple fashion. I'm like keep on basing myself, like let's be there, let's understand one single point, and I try to understand that how I can relate the similar concept with some concept through which you are like very much familiar. So you are very familiar with the spring constant. That's why I am telling you this whole theory. So this is the, you can say, the property of material is there, of solids body is there, like steel rod, iron rod, aluminum rod, copper, silver. If you extend any material by some amount, if that amount is very less, it is an elastic region. Elastic means it can regain its shape, that's it. Elastic word meaning is that it can regain its shape. And if you apply any force, it get extended by some amount. If you release the force, it will get the same shape due to the force which is trying to restore the shape of the body. That's it. Understood? Yeah, equilibrium position means when the restoring force is equal to the external force, after which it cannot go beyond. So here the concept will come, that the concept of stress is entered into this picture, which is from the word sigma. Okay, the sigma is like very commonly used word for the stress. So what is stress? First thing, what is stress, and what is the concept of stress, and how I can apply the concept of stress in any numerical part. So stress is basically defined as, please try to understand, that whenever you apply any force on the body, it can be tensile, it can be compressive. Only two type of stress are there. It can be compressive, it can be tensile. Okay, then I'll define the definition. Okay, means if I have any kind of body is there, okay, let me draw that body, like suppose this is the body. Okay, what I'm going to do, I'm going to pick this up and create more models. Okay, so that I can show you like all type of stress. Okay, try to understand. Let's suppose this is the body which is of original shape. Okay, it is having length L. Okay, it is having length L, and there's a cross section area A is there. Okay, both sides, obviously A is there. Now what you are going to do, I'm going to apply a very small amount of force in this way. Okay, very small amount of force in this way, but this is called tensile stress, or you can say tensile force. Right now it is a tensile force. When you apply a force on this body start stretching. Okay, this body start getting stretch, and it gets stretched by some amount. Okay, so if the body length from this position get extended by some value, okay, get extended by some value, and let's suppose that value is any value, x is there, then can I say from its original length it get extended, its length increases. Whenever its length get increases, you can say this is a tensile stress condition. Okay, there is a possibility that you may apply on this body maybe a compressive force. What force? Compressive. People get like sometimes confused. It's very simple. If you apply the force outward, it get in tension, it get tensile stress, but it's trying to oppose this motion. But if you apply the force toward the body, so it actually decreases its shape or not? Yes, it actually decreases its shape. and it decreases the shape by some amount. Okay. So what happened with respect to the original length? You can see very clearly that here the length is decreased by some x value, here the length get increased by some x value. So this condition is compressive stress condition. Okay, this condition is compressive stress condition, and the above condition is a tensile condition, and this condition is no stress condition. No problem. Okay, he is happy there. Why he is happy? Because at that condition the force applied on the body is actually, there is no applied force on the body, so there is no stress on the body. It is actually like very happy. Okay, understood? So that is basically your basic stress concept. Now come to the, sir, how you define stress mathematically, how you define stress. Okay, I want to understand what is the definition of stress. So stress, they define that stress is defined in this way, that it is the ratio of the internal resisting force, or you can say restoring force. Okay, restoring force per unit cross sectional area. This is the exact definition. I want to give you exact definition because it's going to be useful. So can I say that stress is equal to, you can say whatever the force which is applied on the body, or you can say the internal resistance force, but at equilibrium position the internal restoring force is equal to the external force F divided by the area of cross section. Okay, some people may think, sir, this force is F, this force is F, it should get cancelled out. No, nobody. You can say this is a fixed point, you apply force there only, but this fixed point also applying the force not to remain at this fixed point. Okay, so don't cancel it out. And in actual sense, there is only one force which is trying to get extended. This force is to balance this force at this point. Okay, due to which this body get extended by some value of x. And I am putting this F by A. But sir, the definition is restoring force, but you are putting like force as like F only. See this part. Can I say at equilibrium position? At equilibrium position, can I say the restoring force inside the body is actually equal to the external force or not? Yes. That is what is happening. The restoring force by any molecule to its adjacent molecule is exactly equal to the force which is applied on that molecule. Okay, we need to go like in this way only, because that then only we can actually get into the deep concept. Okay. So the stress is actually divided into two parts. One is what? Compressive stress, one is what? Tensile stress. This is a tensile stress condition in which the force applied on the body will increase the length of the body. This is called compressive stress body, in which the length of the body will get decreased. You are actually trying to compress the body. So whenever you studied about stress, you need to study about strain also at the same point. Strain given by, like, in generally given by epsilon. Okay, given by what? Epsilon. Epsilon is just a symbol. Okay, just a symbol. So what is basically strain? So strain is defined as, try to understand, whenever any force is applied on the body, it actually it may increase or decrease the length. Whatever the deformation is there in the body is basically termed as what? Strain. So strain is defined as the, please try to understand, it is the ratio of the deformation of the body to its original length. Here I am writing length, like sooner I'll change the concept, means whatever the original dimension is there. Original dimension is L. If you apply a force, it get extended by some amount which is X. That's it. So the strain is basically, what is the deformation? So deformation is only amount X, may in positive direction or may in negative direction, to the original length is what? L. So that is basically your strain. So strain become a dimensionless property right now. As you can see, it is dimensionless property. It is nothing, it is a dimensionless property. It is basically what is the deformation with respect to length. Why you are taking a dimensionless property here, which is telling me that what is the change in the length with respect to the original length. Why I am taking this? Very simple concept, sir. If I will not take this concept, then it is very difficult. I need to take this concept. Why? The original length of the body can be anything. See, understand. If the rod is very small and you apply a same force, it may get deformed very small because the extension power is very less. But if the rod length is very big, if you apply a same force, it may deform more. That is the beauty of strain. That's why we took strain. Strain actually neutralize the actual length with respect to deformation. We need to take what is the deformation with respect to this original length. If the original length is 1 kilometer, in that 1 kilometer length of the rod, if it get deformed by very small value, that is called strain. That we need to define the strain. So there should be some common parameter should be there. The common parameter here is like what is its original length. That's it. So I hope you understood what is the strain and stress 2 parameter, which is the whole basis of this chapter. Whenever you are going to study this chapter, you need to just understand these two parameters, nothing else. Okay, if you understood these 2 parameters, everything is done. Okay, then we need to just understand like what type of stress and what type of strains are there. Okay, nothing else. Okay, now come to the next part. The next part is Hooke's law. Okay, highly important. Okay, Hooke's law. Hooke's law is basically defined from the Hooke's experiment. Okay, nothing else. From the Hooke experiment, it is get defined. What was the experiment? I'll show you that experiment as very you can say very good experiment, and through that if we start reducing, then we can actually deduce that concept. Okay, because that concept is very important. We need to understand from the very fundamental law. So it is basically derived from the experiment. What is that experiment? That they took steel rod in 2 sections. Okay, they took one steel rod, okay, like this, attached, other steel rod attached, basically one only the steel rod, but just for your experiment purpose, and they attach some hook into that. Okay, and they put some weight in the second condition. Some weight in the second condition. In the first condition, there is no weight, it's totally blank. Okay, there is a cross section area is there. Okay, this is the length, original length is there. In the second part, what they did, they put some weight on that hook. As they put the weight, what happened? It get extended. And they find out, yes, some area is also get decreased. yes, the length get increase by some amount, but area also get decreases. So he defined in a very simplified manner that I studied experimentally, the stress produced why the stress get produced. Simple thing, sir, as you apply your weight, it get mg weight is there, and that is called the external force for this rod, and due to which this rod get extended. So they said the stress produced inside the solid body is directly proportional to the strain. So he said in very simple fashion, he said whatever the type of stress is there, that is always directly proportional to the strain, and when you remove this proportionality, then you get stress is equal to some constant coefficient, and you can say, let's suppose A into what the strain. Everybody will ask that what is this A is? What is this A? Okay, they said A is nothing. A become the proportionality constant or modulus of elasticity. Okay. So I want to know this, what type of modulus of elasticity is there, and what type of stresses are there, strains are there. Okay. Strain in short, yeah, for sure. Strain is very simple, like it is coming like in detail also, but for your understanding, I am telling you in very simple fashion that whenever you apply any type of force on the body is there, it will get deformed due to that force. When it get deformed by some value of x, you should always understand the concept of strain, because what is the deformation with respect to its original length, and that is called strain. Okay, nothing else. So this is the Hooke experiment that Hooke was doing, and Hooke derived this parameter for every concept, that stress, any type of stress is there, it is always directly proportional to the strain. Any type of stress is directly proportional to the strain. That's it. That is what is defined by Hooke. Okay. So I need to understand now what type of stresses are there and what type of strains are there. Okay. So one by one we'll understand the three type of stress and strain, then we'll combine together into one single short note, so that we can complete this chapter in one page. That should be our target, like for every chapter that is our target. Okay, we need to understand in a very simplified manner. So the first parameter of type of stress which come into your the concept was very beautiful, you can say the parameter after the Hooke experiment, and which is done by, you can say, Young's, and maybe you heard about Young modulus, maybe not, don't worry. That came into the picture, that was actually came into the picture. So what is Young modulus? Okay, it is coming from the concept of longitudinal stress and strain. Longitudinal stress and strain. Basically we need to understand, like I'll tell you first, basically there are three types of, if we talk about types of types of stress, okay, and strain, there are actually 3 types majorly. In strain, yes, there is a one more type is there, but in stress the only major 3 types of stress and strains are there. When you talk about stress, there is one is what? Longitudinal stress. Its symbol is sigma always. One is your shear stress. Is normally sigma is tau. And the third one is volumetric stress. Its symbol is sigma V. When you talk about strain, majorly there are 3 types of strains are there. First one is, if the longitudinal stress is there, then longitudinal strain, symbol is epsilon. Then there is a shear strain is there, okay, and its symbol is sometime we use as gamma. I can use different symbol also, okay. And the third is volumetric strain. Okay, volumetric strain, where symbol is epsilon V. Okay, so what I need to do is I need to just understand from a basic point of view. I don't need to make it very complicated. I need to understand from a basic. So that's why I'll tell you about this 3 parameter. First one is, like from its name itself, you can understand longitudinal, along the length, whatever the happening is there. Strain and stress is just the 2 phases are there numerically, but the concept of longitude you need to understand. There is a concept of shear is there. Whenever you talk about shear means like whenever you trying to shear the body, means whenever you are trying to destroy the shape of the body, whatever the shape distortion is there, that is comes under the shear stress and shear strain equation. Volumetric strain is very similar to longitudinal, but in a volume basis. Like if you, like in 3D world, if there is any object is there, if you apply the forces from all the possible direction on that body, it will get into volumetric strains and volumetric strain part. That's it. So if you understood one very basic fundamental, and that is basically your longitudinal stress, then the game is over. Okay, then you can complete everything. Don't worry about it. Understood? Okay. Done? Chalo. Now we will start understanding. Sir, whenever you talk about longitudinal stress and strain, I need to first understand that who derived this. Like that is the most important part. And basically from that, my classes is scheduled. Please check in my profile. Okay, now understand. Please see this part. Sir, if any body is there, like this body is there, and let's suppose like attached to some fixed point, because I need a fixed point there. Okay, now I am going to put another body there. But this is not a new body, this is the same body. It's just a representation for you. So this body, like dimension, I'll first explain. This body dimensions are: L is original length, its cross sectional area, okay, and you applied a force along its length, along the direction of length, or you can say perpendicular to the area of cross section, perpendicular to the area of cross section. Okay, let me check with the team. Okay, if the class is not scheduled, let me check with the team. No need to worry, for sure. Okay, chalo. So what I need to do, I need to just understand what is longitudinal stress and what is longitudinal strain in very simple fashion. So what happened, when I apply a force on any body which is having original length L, the cross section area is A, what I found out that it get deformed by some value of x, okay, and till the point it get extended, till the point this F gets control due to the some internal restoring force, due to the some internal restoring force inside the body. When this restoring force is get equal to this force, then this body gets stopped at this deformation. When this process ends, you can now define each and everything, and now it's defined by this method. Now the longitudinal stress is get defined and symbol is always sigma, okay, and it is equal to whatever the restoring force per unit area is there, that's it. But the restoring force is equal to the external force F, that's why I can put F by A, that's it, finish. My problem is done. When you talk about longitudinal strain, similar concept, same concept, that is given by epsilon, the ratio of the deformation for its original length L, whatever the deformation there with respect to original length L, that's it, finish. Okay, that's it, finish. Understood? As per the Hooke's law, as per the Hooke's law, which is valid everywhere, can I say stress is directly proportional to strain? Yes. Now this proportionality get removed, and it removed from one very beautiful parameter, that stress is equal to capital E into epsilon. And everybody starts speaking about this capital E. Who is this capital E? Who is this this is coming from a very young scientist. That's why it's named as what? Young's modulus. Is no, the scientist name is basically Young. Okay. Okay. Yeah, schedule for both. I think Raftar batch schedule is like publish. I need to check for Nimbus. Today only I think Raftar batch get published. I'll check for sure. Just after this class, or I'll take the break when I give the question, then I'll check with the team. So Young's modulus is basically the proportionality constant. It is also termed as what? Elastic modulus. It is also termed as what? Elastic modulus, and plays a very important role sooner. If you just open the whole symbols, what is stress? F by A. What is elastic? E. And what is epsilon value? That is deformation by length L. You can determine this E value, and also you can also determine this thing, that what is the value of X, the deformation value. Can I say that is FL by AE? And it's a very important formula. You will get to know sooner. This is the deformation value in any rod, that whatever the force applied, what is the length, what is the cross section area, and E is very important. That is basically Young modulus or elastic modulus in the solid part. Now come to the dimension part. Can you tell me for stress what is the dimension? So very simple, force is Newton. Okay, force is what? Newton. area is what? Meter square, Newton per meter square. That is basically your stress. So can you tell me what is the dimension for stress? Sir, very simple. What is the dimension? What is the dimension for force? Sir, mass into acceleration means m L T minus 2, and you need to divide with the area. What is the area dimension? L square. If you divide with L square, this L become what? L minus 1. That's it. Can you tell me what is the dimension of strain? Dimensionless property. That's a beautiful part. If somebody asks you that what is the most important dimensionless property in solid, this is the property that is called strain inside the body. Okay. Okay, Shakbo, I'll check. Yes. If the force value F gets stopped, if you remove that F value, the body will regain its position. It doesn't have any kind of stress. It doesn't have any kind of deformation. If somebody will ask you what is deformation, you can say that X value is the deformation value. And I want to postmortem this whole concept and derive everything. So right now you studied that stress is equal to what? Young modulus into epsilon. This is a very important equation coming from the Hooke's law, but the E is a property of the material. E will be given to you always. Okay. What is stress? Sir, force by area. What is E? Is a material property. What is epsilon? Deformation by the length. Can I say something? That can I say force is equal to nothing? Sir, AE by L into X. Yes. Can you tell me what is A, E and L? Sir, A is the cross section area, E is the Young's modulus, L is the length of the rod. So these three are the first defined properties. If I want to convert into spring, so that is called spring constant, and the spring force is equal to what? Kx, that you studied in the spring chapter. So can I say if any rod is there, can I assume that, can I convert this rod into a spring system? Yes. So you apply a force F here. If you apply a force F here, or if you apply a force F here, whatever the deformation in this rod is there, whatever the deformation X in this rod is there, whatever the deformation in the spring is there, you can define this K on, or you can define the length, original length, its area of cross section and Young modulus for the rod. Both are same. This is called spring equivalency. That's actually a separate chapter, but I am not separating this chapter. I am teaching you here only. Arey, it is nothing, yaar. I can assume this rod to be a spring because very simply, if this rod is there, if I apply the force, it get actually deformed by some value. If I remove the force, the body will regain its original shape. This is happening only till the point of elasticity. Elastic means when it can regain its shape. Plastic means when it cannot regain its shape. The shape is get deformed permanently. Understood? So this is nothing. This is a kind of note for you, like how I can relate a actual rod concept, okay, to the spring concept. Obviously, if you want deformation, the spring force is equal to what? Kx. Deformation is Fs by K. The K is a constant property which is E by L. They may ask you in any examination. A lot of problems are there. Okay. That is basically your concept from the longitudinal stress part, okay, and the strain part. There's a one more important parameter that you need to study here, okay, very important parameter, that is lateral strain. Beautiful parameter. Why I need to study this? Okay, this is basically, that is longitudinal, and this is what? Lateral strain. Lateral strain you can define like with respect to, you can area. So I can put it like epsilon A for my condition, because sometime they may change. So what is lateral strain? I need to understand. And then when I understood the lateral strain, then I want to understand one more parameter, and that is called Poisson ratio. Okay, let's remove the Poisson ratio for right now. Okay, I'll put in the next note, but I need to understand the lateral strain part. Very important. Is there any problem that may came from this Poisson's ratio? Okay, that I need to understand. That what is the point which is coming from the Poisson ratio, from the lateral strain part. Okay, but before entering into this part, I want you to understand one more parameter, okay, which is basically the volumetric strain. Before completing this volumetric strain, I cannot like teach you that the most important functional part, okay, that needs some time, like in this space, highly important. But obviously for volumetric strain I need to just stay for some time, then only I can go through that. I cannot go through like directly, but I can try, and that is what I am going to do. Okay, clear? Young's modulus of elasticity or something like that. So what is happening with respect to other type of stresses are there, when there is other type of stresses are there. So what is other type of stresses? Okay, that we need to understand. So I understood the longitudinal part very clearly. Okay, now I need to understand the shear part. Okay, I need to understand the shear part, that what is shear stress, how I can understand the shear part, and then volumetric. If you understood these three parameters, you can solve any type of problem, whatever the problem you want to understand, you can solve that kind of problem. Okay, okay, pakka. Chalo, let's understand this part. Okay, we'll come here, don't worry, because I already put the topic. I want to teach you two things. One is this, and second is Poisson ratio. Okay, but before entering into this, I have to teach you second type of stress. Okay, that is called shear stress and strain. Shear stress and strain. So for that I need to understand from the first, from the you can say the 2D part, 3D part, and then I need to understand from the 2D part, because like problem may came from any type of parameter. Now understand this part, okay? You need to understand each and every parameter clearly here, because if your dimensions are also like get disturbed, the whole concept get disturbed. So let's suppose this rod or this body is having this length as L, okay? This is some width is there and there is some height is there, okay? So this is the W width and there is a height H is there, okay? What happened? Let's suppose I just make the bottom surface to be a fixed surface. If this surface is get fixed with the ground, what happened? You cannot move this body, but can I destroy this body? I know if I apply a force in this direction, it get increases length, like this H height will increase, but I am not focusing on that part. I am focusing on something else. I am telling you that if I apply a force, if I apply a force in this way, you know what is this force? This is a force which is parallel to the surface area. This is called shear force. This is called shear force, Fs. You know what happened due to this force? Of cross section. Okay, the area perpendicular to the Fs. Area will correctly if I say area vector. This is the area vector is like perpendicular to the shear force, or you can say the Fs is the parallel force to the area. When you apply this force, what happened? Basically what happened, this body get distorted by some deformation of the shape is there, nothing else. Some deformation of the face is there. This body get deformed. I hope you all can see the deformation clearly. This whole body get deformed by some value, okay? And this deformation x is there. It get deformed by some x value, even though it is having some original height is there, or you can say original length is there. It doesn't matter to me. But there is a original and it get deformed by some value, that is value of x. This deformation is in which layer? Can you tell me in which layer? This is deformation on the top layer. If you see the deformation and other layer, it actually changes. But what is not changing? This theta. That is called angle of deformation, or even in very simple word, it is called shear strain. That is called shear strain. If you see here, this point is fixed, but after that certain point, some deformation is x, some deformation x, some deformation x, so these every layer having a different form of deformation. But with respect to this h height or not, with respect to this length from the fixed point, the farthest point is more deformed, the lowest point is not deformed. Every point is differently deformed, but the angle of deformation is same for each and every point. Okay, but the angle of deformation for each and every point is as it is same. and from here they define the one of the most beautiful parameter, that is called shear stress. The symbol is, you can say, gamma. The shear stress is, tau, is the shear force applied on the body with respect to area A. The force applied on that area layer. And the shear strain which is symbolized with gamma, is basically what? It is the deformation, like previously the deformation, the extreme deformation on the layer where the force is applied with respect to the length from the fixed point, means x by h, or in very simple word you can say it is equal to tan theta, and the theta is so small that you can put it at theta. See, please try to understand. That's the beauty of mathematics, that if any quantity is very, very small, the sin theta become theta and the cos theta become 1, because cos 0 value is 1. So if 0.01 degree is there, you can say cos 0.0 degree 1 value is also 1 value, but sin 0.01 degree is not 0. You can say sin 0.0 degree value when the sin theta is very, very small, because that is equal to theta only, bhai. Just put it theta. Whatever the theta value is there, the same thing is what? Shear strain. And when you define this, the Hooke's law came into the picture. So as per Hooke's law, can I say the stress is directly proportional to what? Strain. The only parameter difference is what? Now it's shear stress and this is shear strain. So now the new picture, new modulus come into the picture. You can put like any symbol. Some people are putting mu, some people are putting neta, and you can put anything. Then this tau, it is equal to eta gamma. Symbols are getting tougher, the concept is as it is same, the only understanding is needed. See, please try to understand, you need to understand. You need to understand. Okay, I'll explain, don't worry, just complete one time the topic, I'll explain you everything. This neta is now defined as the modulus of rigidity. Why? First thing, my questions are like this only, why it is termed as modulus of rigidity, or some people are saying it is called shear modulus. I can understand this is called shear modulus, like elastic modulus, but why it is termed as modulus of rigidity? What is rigid body? Rigid body never deform its shape, even the application of any amount of force. That's why it is called modulus of rigidity. That if you apply any force on the top level of the solid material, it actually get deformed. When it get deformed, it is like lesser rigid body. If you want more rigid body, it should not get deformed. The deformation should be almost 0. Can you tell me when the deformation can be 0? When tau by neta should be equal to 0, then the gamma is 0. And when the gamma is 0, the tau you cannot make it like 0. Tau should be there, like application of force should be there, but neta can make it to infinity or not. So whenever any body is having more and more neta, means this body is having more and more shear modulus, or you can say the body is difficult to get sheared by any force. Very difficult to get sheared by any force. What is the difference between shear stress and shear strain with respect to longitudinal stress and longitudinal strain? I will tell you in very simple word, try to understand. In this, you apply a force which is perpendicular to the cross section area along the length of the body. The length get deformed, that's why it is called longitudinal stress and longitudinal strain. the length get deformed completely, the shape didn't get deformed. But here in shear word, why it is called shear? Because it is kind of shearing the layers or not. It actually sheared the layer. It is actually distorting the shape of the body. If it is in elastic region, then if you like put this body in this way and then remove the force, it will regain its position. And you can check this on your any book. If you take any book, try to hold it from the bottom and try to slide your hand above the book, it actually deform its shape. But if you remove your hand, it regain its shape. Okay, but every page of that book, if you try to shear every page of the book, it actually sheared by some other value. The only common parameter is this theta is same for every level or every layer of the book. That's why this theta is very important. That's why this theta becomes shear strain. Okay. See, whatever we studied, I want to apply my question series. Okay, so this is the mechanical properties of solids, all the PYQs for the JEE Mains and Advanced both. For the JEE Mains and Advanced both. Okay, please try to understand. See the problem. It is coming from JEE 2024 and the problem is highly simple. Please try to understand. Two person pull a wire toward themselves. What is happening? That there is a wire. Okay, there is a wire is there and they are trying to pull it toward themselves, means they are trying to apply the force FF. Can I say this is called what kind of stress? This is called tensile. It get extended by some value of x or not? Yes. Each person exert a force of 200 Newton. Okay, this force is 200 Newton. Thank you. Okay. On the wire, the Young's modulus of the material of the wire is this much. What do you mean by Young's modulus? Or you can say the modulus of elasticity, that is called 1 into 10 power 5 11 Newton per meter square. Why this is the important? Because that is called property of material. It is coming like from experiment only, you cannot derive it. It is what? It is the proportionality constant of the Hooke's law. Hooke's law said stress directly proportional to strain, but you remove the proportionality, sigma is equal to E epsilon. What is this E? Young's modulus. But this is for longitudinal stress along the length. Yes, along the length they are stretching this wire. The original length of the wire, original length of the wire is also given as 2 meter. So 2 meter is the length of the wire and the area of cross section is also given, which is given as what? 2 centimeter square. Okay, nice. The wire will extend by length in how much? They are asking about this x value. Can you tell me what is stress? Sir, force by area. Young modulus. What is strain? Sir, what is the deformation divided by its original length? What they are asking? This x value. So x value is what? Sir, FL by AE. That's it, FL by AE. What is the force that you applied? Sir, force I applied as 200 Newton. What is the length of the rod? Sir, 2 meter. SI unit only. Okay, what is area of cross section? The 2 centimeter square. 2 into 10 power minus 4. Why? Because 1 centimeter is equal to like if you divide the 1 centimeter by 100, you will get 1 meter square. And what is E? Sir, E value is 10 power 11. So this 2 will be gone with this 2. So the x value will be, so this 10 power minus 4. If you take this 100 value also, this is 10 power minus 6. 10 power minus 6 with 10 power 11 is 10 power 5. If you put it above, it becomes 10 power minus 5. They are asking in the micrometer means 10 power minus 6. So can I say 20 into 10 power minus 6 meter, or you can say the x value is 20 micrometer. Can you tell me if I put in, let's suppose if I want to put in like in centimeter, millimeter only, then it is should be divided by 1000. So it is 0.2 millimeter. For the 2 meter long wire, you can only get 0.2 millimeter or not. Yes, yes, yes. Correct, Sai Shiv. Okay. So that is the value of x. The solution will be given to you, but the whole point is the way in which the solution is given in the examination, like in many places, in many books, and the way I am doing it, like slightly different, but the concept is same always, and I am getting the answer very easily because I am not like putting the delta thing. I know this x value is very, very small. X is deformation. So that I can relate this concept of the, this whole chapter I can relate with one very simple concept of spring. Is kind of spring condition or not? The only thing changes here is the spring constant is not given. Other, like apart from that, Young modulus, area of cross section, length of the wire, this parameters will be given to you, nothing else. Okay. So the overall the concept is going to remain same. Concept is not going to change. You can see like nothing I need to remember, all the data will be given. I just have this whole chapter is based on Hooke's law and your understanding of the type of stresses. That's it. I'll define, like in the end I'll define everything in one go. Let's see one more type of problem. Very easy, we'll do that, don't worry. Okay. Okay. Okay, we'll do that. We'll do the pulley quotient obviously. Oh. See, for this type of problem, what I need to do is very simple. So it's a very fundamental problem. It is basically, if you see the whole concept, you will get based on only simple parameter of the longitudinal stress. The only thing that you need to understand here is the fundamental part, that how you can relate your same concept with respect to, but you need to understand volumetric thing also, but without volumetric thing also you can solve this problem. So what is this problem? Please try to understand. Two metallic wire P and Q. Okay, so there is a one metal wire is there P, there is a one metal wire is Q is there. Okay, have the same volume. Please try to understand, if the volume is same and are made up of same material, if material is same, what do you mean by that? Sir, the Vp volume is equal to Vq, first thing, and second thing, if the materials are same, so the Young modulus in the P is same as Young modulus of the Q, because the Young modulus is the property of the material. Okay. Now come to this part. If the area of cross section are in ratio of 4:1, okay, the area of cross section of the P with respect to Q, okay, with respect to Q, area of cross section of the Q, it is in 4:1, and you know the volumes are same. If the volumes are same, can I say what is the ratio of the length? Sir, area of the P into length of the P should be equal to the area of the Q and the length of the Q. The area of P by Q, the AP by AQ is basically 4. So can I say 4 times of LP should be equal to LQ or not? Yes. So this is the second important parameter, the length ratio I know. Okay. And the force F1 is applied to the P, and extension of delta L is produced. The force which is required to produce the same extension is Q is F2. Then what is the ratio of F1 and F2? See, understand. They said that the extension should be same. The delta L or the deformation should be same. Can you tell me what is this? So stress is Young's modulus into strain. Stress is force by area into E. The strain is what? Deformation by original length. So the deformation X, or you can say delta L, should be equal to what? FL by AE. They are saying the deformation should remain same. So they are telling you that delta L for P should be equal to delta L of Q. What is delta L for P? FL by AE. So I am going to put FL by AE. It should be equal to FL by AE. Sir, this is F1, this is F2. This is LP, this is LQ. This is AP, this is AQ. And this is EP, this is EQ. The E will be gone. Why the E will be gone? Because it is made of same material. When you talk about LP by AP, or you can put directly also, let's suppose LQ is L, then LP is what? 4, L by 4. Simple. Or you can say the LQ by LP is 4. So this is LQ, this is LP. Okay. I want to know what is F1 by F2. So can I say this is LQ by LP? You know what is LQ by LP? This is 4. And the other parameter is AP by AQ. AP by AQ is also 4. That is also 4. So if you multiply 4 with the 4, you will get how much value? So 16. So your F1 by F2 is 16. Done. What I used? Nothing. Only the change of the symbol is there. Hi Vikram Reddy. So if you see any type of problem here with respect to strain, as you can see we studied this much only. We need to also study like slightly more. From this much only we can solve almost like 50% JEE problem, because the 50% problem is coming from longitudinal stress, longitudinal strain only you can solve, and almost like every year there is a one problems. Okay, 2024 like very basic, we'll solve, don't worry. Potential energy problem will solve, don't worry. We'll solve each and every one, don't worry. We'll go with each and every problem. I want you to solve this problem from the JEE 2023. We solved almost like JEE 2024 all problems. Now I want you to solve this JEE 2023 problem. Okay, then only we'll move. But before getting moved to the next part, I need you to give an understanding. I'll show you the problem, but I need to give you the understanding of one more thing, that yes, we studied about shear stress and shear strain in very simple fashion. We need to also understand about one more parameter. Then we can go for like all type of problem, don't worry. Okay, then we can go for all type of problem, but we need to understand like slightly more, very not too much but very less, but yes, we need to understand. Because see, very simply, if you don't understand like the ending point, okay, and the ending point, then it's going to be very, very difficult. And that is your last part. Okay, last type of stress. Only there are 3 types of stress are there. That is called volumetric stress and strain. Volumetric stress and strain. if you go with the name of the volumetricity, you will find out that what do you mean by volumetric stress and strain. Very, very simple like. Okay. Whatever you studied in your basic fundamental, the same parameter will be there. Okay. No need to worry. No need to worry. Like very simple, very simple. Okay. So try to understand what is volumetric. And it is going to be highly useful in the this next chapter also. But to have an understanding, we need to understand like what is volumetric stress and what is volumetric strain from the two shapes of the body. First, I will take the spherical shape, okay, and then I will take the cubical shape. But still, I show you from the both end. But we need to start from the spherical shape body. Okay. Let's suppose there is a sphere is there. Okay, there is a sphere is there. This is a center point. So this is the whole body is there. If you talk about this sphere, how you can show the sphere? This is the way to show the sphere, that this is the sphere. This sphere is of radius r, or you can say a small r. Okay. So can you tell me what is the volume of this sphere? So the original volume of the sphere is 4 by 3 pi r cube, or you can say capital R also. No need to worry. Can I through any process, can I decrease or can I compress this sphere, or can I extend this sphere? Very much possible. If you put this sphere inside any fluid very deeply, what happened on this sphere? The pressure will apply from every direction. Whenever there is a pressure change is there. See, I am not talking about pressure, I am talking about the pressure change. Pressure is nothing, the force per unit area. If there is any delta P is there, which is basically the force per unit area change is there, then what happened? The whole shape of the body will remain same. The shape will be remain circular only, or you can spherical only. If this sphere is initially, if this is a spherical body, it will remain spherical body. It is not going to change its shape, but it will undergone the change in the, you can say, the dimension of the body. Okay. The dimension of the body. See this part? Yes. What happened? This body will undergo the change in the shape. The white body was the original body, but what happened? It will undergo the change in the volume, not in the shape. Change in the shape changes spherical, that is going to be shear stress. But if the body will undergo the change in the volume, that is called volumetric thing. Try to understand. The concept is not going to change ever. Now the volume is get changed. The volume get changed. The volume is decreased. The volume is slightly decreased. Initially, let's suppose there is a V volume is there. Now the V dash volume is there. Some other volume is there. I can see very clearly there is a volume change. So in volumetric stress condition, most important point, shape of the body is same. Same means spherical, but there is change in volume. Change in volume. From this condition, the volumetric strain come. You know what is stress? Force per unit area. The change of force per unit area. Similar in the fluid part, the force per unit area is delta P. That's why it is called volumetric stress. I already told you like this parameter will come more in fluid mechanics, but yes, it will come. You can't avoid it. You need to solve it. Okay, that is the most important point. You need to solve this. You need to go through this. You cannot directly ignore this part. You apply a force on the body, it will undergo the change in the shape. Change in the shape for sure. Sorry, change in the volume is there. So that change is basically the volumetric stress, nothing else. So volumetric stress basically the delta P directly, but it is compressive in nature. Yes, it's compressive in nature. That's why it actually decreases volume or not. Yes, that's it. Okay, that's it. That's why it will decrease its volume. Okay, and through that volumetric strain will come. I am going to like put this symbol as sigma V also, and this is epsilon V, this is going to be very useful. That is basically the change in volume with respect to the volume. In this condition, if I apply Hooke's law, can I say that delta P, or you can say the volumetric stress is directly proportional to what? Minus of delta V by V or not? Why I am putting minus here? Very simply, you are applying the force in the compressive nature. That's why there is a decrement in volume is there. So delta V is minus. That's why I am putting minus. So the minus minus will cancel out. You will get a fixed positive value. And when you remove the proportionality, you will get delta P is equal to there is a concept called bulk modulus minus K delta V by V. There is a lot of symbols are there for bulk modulus, like people are using different symbol. I am using this symbol. You can use this same symbol for this part also, that sigma V, thus volumetric stress is equal to K times the epsilon V. Same. Why I am not putting minus here? Why I am putting minus here? I know in this fixed condition, when you apply a pressure change, there is a change in volume which is lesser, which decrease the volume. In this my condition, that's why I am putting minus, so that it will remain plus. In this condition, the general form, obviously whatever the stress is there according to change in volume is there, I need to put it as a positive only. But the most important part is this K. You know this K is called bulk modulus. Bulk modulus of elasticity. Many people get very difficulty, and when you talk about in order of remembering this, that bulk modulus is here, there, and that kind of stuff. Very simply, here what is happening in bulk as a whole body, its volume get decreased. That's why it is called bulk modulus. When along the length get decreased, that is determined by scientist Young. That's why it's called Young's modulus, or you can say simple elastic modulus. When applying a shear force and it is shear the shape, it actually distort the shape. That is the based on rigidity of the body. If your body is not rigid, it get destroyed. It gets sheared. That's why the shear, you can say shear modulus of the body, or you can say simply the rigidity of the body, or rigidity modulus. That's it. Okay. Yes. So this is a kind of example for liquids. But if I apply an example for solid, and I actually want to apply a example for solid, Can I take some example which can help me out? Yes, let's suppose, okay, let's suppose there is a cube is there and I am solving one numerical problem. Please focus, okay? I am solving a numerical problem. I need your focus, guys, okay? This is the sphere, proper sphere is there whose length is A. So can you determine the cross section area? It is basically a sphere, sorry, cube. So for cube, when there is a one dimension is A, all the dimensions will be A. And if I apply a force here as F, try to understand, front of the axis F force is there, back side F is there, top side F force is there. Can you tell me what is the type of force that applying on every face? That is F. What is the cross section area at every face? That is A. So can I say F by A is the constant value of the stress I am applying on this whole volume or not? Yes. Due to which this sphere get compressed and its volume get decreased by some value. The volumetric stress is directly proportional to volumetric strain, and when you remove the proportionality, you will get bulk modulus. Can you tell me the stress on one surface, the force by area, that is the volumetric stress or not? Yes, because the same force is applied in everywhere. What is the change in volume? So change in volume is the change in the volume with respect to the original volume. The original volume is A cube. The change in volume is some change in A is there. So this is for solid body. This is called hydrostatic condition. But I don't want to tell you that hydrostatic condition right now. But yes, there are certain conditions named as what? Hydrostatic conditions. Okay. Okay, tell me. To get the concept here. Okay, that is something I want to you have an understanding. Okay. So this is the condition for volume, and when you going for to solve the volume problem, you will get surprised by a lot of parameter. I am telling you very seriously, because this is the only tough part. So I want to enter into one very important part which we left is lateral strain and Poisson ratio. You know what is lateral strain? Even Poisson ratio I can define here only in the same way. Please try to understand. Let's suppose if I have a body whose cross section area is A and its length is L, can I say the volume should remain conserved or not? Yes. If this body is fixed with the wall and if I apply a force F, what happened with this body, the solid body? Sir, it get extended. Okay, if it get extended by some value of x, or delta L, see nothing, this x deformation is the change in the length or not? Yes. When it extended by some value of length, okay, delta L, or you can say the x value, the deformation value from its length, can I say that the areas also changes or not? Yes. The area is not going to remain the same. This is, let's suppose A dash is there. So can I say the original area was this much with the dotted line? This was the original area. Can I say the area is actually get decreased? Yes. So there is a delta A in the cross section area. Yes. Or from this part, the concept of lateral strain is actually get produced. That is there change in the area, is there or not? Yes, delta A by A, and the force is not applied in that direction. The force is not applied in this direction, that area should change. But yes, still the area get change. Okay. 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 Understood? So the area value is actually get changed. The area value actually get changed with respect to its length. Okay, with respect to its length, the area value get changed. Okay. With respect to its length, the area value get changed. That change in the area with respect to original area, it's called lateral strain. Longitudinal strain is different, lateral strain is different. So that is called lateral strain. And from here, one more concept being created. And what is that concept? Please try to understand. Very, very important concept. And if you get the concept feel, you can solve any type of problem. And that is a concept of Poisson ratio. Concept of Poisson ratio. Highly, highly important. Rarely the problem, and in advance the problem is fixed. If the problem is coming from properties of solids, then obviously it is coming from the Poisson's ratio only. That is a conceptual part. You know what is Poisson ratio? There is a scientist named as Poisson. He explained this ratio, that whenever on any body, you apply, any sort of, any type of, any method of, yes, any method of, any way of strain on the body, its length will increase. Okay. And the ratio of, it is nothing, it is the ratio of lateral strain to the longitudinal strain. So basically it is defined with the mu, that is basically epsilon, you can say lateral to the longitudinal. This is depend upon the shape of the body, okay, and the minus sign is there. Why? Because it is going to be of opposite nature. If the length is increased, the area should or the radius should decrease. If the length is what? Increase, the area or the radius should decrease or increase. Now if you know the concept also, but if you don't know like how to solve the problem, it's going to be very, very difficult in very simple form. So that's why now we need to enter into the problem solving method. Okay, without that you cannot, without that you cannot. Yes, correct, Tanisha, correct, Sai. See, if you don't understand this concept, like, but for the proper understanding, I need to put some note here. I need to solve the problem. When I start solving the problem, I can go back to this part and I can solve like n number of problem here. So like in short, if I put in short, I studied about, basically in short, like completely, if you talk about, I studied about 3 type of stress. Okay, I studied about 3 type of stress. Okay, what are the 3 types and how they are related to each other? So first one, I studied about 3 constant also. I studied about 3 constant and 3 type of stress. What are the 3 type of constant I studied about? The first constant I studied about Young's modulus, which is coming from the E part. Okay, which is E part. You can say Young's modulus. Second part is shear, from shear stress condition. Okay, that is basically termed as what? Modulus of rigidity. Okay, sorry, this is modulus of rigidity, eta, or you can say shear modulus. There is a relationship between them, but it is in the strength of material part, like solid mechanics, which is like higher end, which you are going to study it when. Okay, I'll clear. And the third one is K, which is called bulk modulus. They all are coming from different parameter. When the longitudinal stress directly proportional to longitudinal strain, you will get this proportionality. Sigma is equal to what? E epsilon. This was the step, and it's a material property, completely a material property. When you talk about shear, then the shear stress directly proportional to what? Shear strain, which is basically theta also. So that place, when you remove the proportionality, you will get this eta part. Okay, we need to talk about bulk, then the volumetric stress when directly proportional to volumetric strain. When remove the proportionality, you will get the bulk modulus, like as a bulk how they are acting. Okay, so these are the 3 parameters that we studied, like with respect to stress. There are 3 type of stress are there. One type of one strain we studied also. Here the stress is what? Force per unit area. E is E. Epsilon is either delta length, change in length by original length, or you can say the deformation part. Through that you can determine the deformation x or delta L as FL by AE. And if you see the like very focusedly, if you see all the parameters, the L, A and E are constants. Okay, this is the way you can find the deformation part. Here the tau, when you talk about tau, the force which is parallel to the area of the shear area, you can say the AS is equal to neta, and the shear strain is the basically the deformation x by L, or you can say it is equal to what? N theta. The shear strain you can put directly as theta, that is shear strain. So the shear strain theta you can get directly by F parallel to the shear area into what? This eta property. Okay, that is called basically your shear modulus. That's why shear modulus is important. In volumetric stress, when you mostly in the pressure condition, so that stress is what? The change in the pressure per unit area. Pressure is basically per unit area, force per unit area. K is what? Delta V by V, but there's a minus sign is there. And here, if you want to determine what is the change in volume is there, that can be delta P into V by K in minus. Minus shows like change in volume if it is negative or not. If it is a negative, it come out to be as negative only. But here, this is not important when you talk about problems. I'll show you, don't worry. What is the most important part here is this. Please see this part. There's a one more parameter is being defined here, that is called compressibility. Ability, which is defined with the C, and it is equal to 1 by K. So what is K? Delta P V by delta V. So what is C? C value is basically C value is delta V by V, okay, into 1 by delta P in minus. What is the feeling of this part? That compressibility is also a parameter, that how much force per unit area, means the pressure you applied to the original length, and how the change of the length is there. If the change of the length is very, very high, the body is more compressible, or you say its compressibility is more higher. If compressibility is higher, it's basically bulk modulus is lower, or you can say it's the resistance against the type of pressure through which it can decrease the volume or not, it is basically less. Yes, correct, Tanisha. Okay. Yes, I see, don't worry. Minus sign just signifies, see, this is the general formula. Minus sign here is why? Because when you apply a pressure on any surface, its volume get decreased. When the delta V is minus, I don't want the value should be shown as minus, that's why I am putting minus, like just for sign convention, nothing else. Okay. But when you start solving the problem, then only you will get understanding. So this is kind of a short note of the 3 parameter. And there's a Poisson ratio is also there. Okay, Poisson ratio is what? Lateral by longitude. And they can ask you Poisson ratio directly, okay. Poisson ratio, why the minus sign is Poisson ratio is there? Because if you increase the length of any body, if you increase the length, the area will decrease, obviously. That's why minus sign is there. Okay. Now the best part is, let's start solving some beautiful numericals. Then only you can solve, like, a lot of problems. Without that you cannot. I need to teach you a few important condition, but before that you need to have an understanding that what sort of problem they may ask you. Okay, energy problem will do, don't worry. Nothing, see, whatever we studied till now, they are going to ask you from that part only. They cannot ask you from like differently anything. So this was the problem which I going to give you, but I'll give you something else also. Okay, so this is a very nice problem. I want each and everyone to solve this. Okay, because then your level of confidence for solving any sort of problem will increase, like beyond a certain point. Okay, please start solving this part. So this is the problem that you guys need to solve. Okay, and I am taking break, 15-minute break with this problem. Okay. Solve. Yes, Ankit. So this is the problem that we are trying to solve. Okay. In a very simple way, not in a difficult way. Because see, through this problems only you can like get the maximum concept. Okay. What is this problem? What is the problem is all about? Your fundamentals. Better the fundamentals, better will be the understanding. Okay. So what is given in this problem? Please try to understand. A certain pressure P is applied to a 1 liter of water and 2 liter of a liquid separately. Means the pressure is same in the both the condition of the water and the liquid. So let's suppose there is a water condition is there, okay, and there is a one liquid is there. The difference here is the P pressure is same in the both condition. Here the volume is 1 liter, here the volume is 2 liter. That's it. The volume is 2 times. Okay. So if you want to put like liter in some quantity, you can put the value, so you need to worry. Water get compressed by 0.01%, whereas liquid get compressed by 0.03%. What is the ratio of the bulk modulus of the water to the liquid is 3 by x. What is the value of x? So this question is highly simple. The value of x is 1. I can give you the answer directly. Okay, but obviously for your understanding we need to solve it correctly. Can you tell me what is bulk modulus is coming from which direction it is coming from? Sir, coming from the volumetric stress condition. Try to understand. Basically when you apply any pressure, the liquid get compressed and there is a bulk modulus is there which create the volumetric strain of delta V by V. That's it. Okay. So can I say the bulk modulus is nothing, it is minus delta P divided by delta V by V. Whatever the pressure change you applied or the pressure you applied with respect to change in volume to the original volume. That's it. Can you tell me what is the bulk modulus for water with respect to bulk modulus of the liquid? Sir, can I say what is the bulk modulus of water? I am going to put the water minus delta P divided with delta V by V for the water minus delta P divided by delta V by V for that liquid. This is for water, this is for liquid, and as you know in both the condition the pressure is applied same, minus will be gone. So it is basically inverse of this volume changes. Can you tell me volume change with respect to volume it is given in the problem directly. They say water get compressed to 0.1%. If anything get compressed by some percent, what is that value? Sir, if it go up, so delta V by V for liquid to the delta V by V of water, if I want to put for liquid it is 0.03%. So 0.03 divided by 100, that is a fraction or not? Yes. Divide with the, what is that percentage of the water? The water percentage is 0.01, so 0.01%. So if I want to put in value, I need to divide by 100. If anything in percent, like 7% marks you got, what is the exact marks you got? 7 divided by 100. In 100 you get 7 marks. So this 100 will be gone. If you remove the point, it is equal to 3. They said this value is equal to 3 by x. So what is the value of x? So x value will be 1. Okay. I think 1 hour chapter is remaining. Then we can go home. It is basically for 3 hours. Properties of solid. Okay. So this is the exact solution. Now we can go to the next problem. I'll show you the graph first, then we'll solve this problem. Okay. Okay. I want to show you some numerical problem with respect to the shape part. Yeah, shear problems. Yeah, this is a very good problem. I'm going to solve this problem, don't worry. Rod, heavy rod of 20 kg cross sectional length, fixed support, neglecting the lateral contraction, the elongation in the rod due to its own weight, something like weight problem. Okay. So like similar problem, but now the graph problems are too much, so I need to go back to the graph things. Okay, I need to teach you the graph part. Okay, and the weight part, 2 parts are there, and energy. Yeah, so almost like every part is done from fundamental. Now I need to just relate all this part to you. Okay. How can I solve? Like this, see, this is the simple thing. What is the change parameter? Value is there, na? Like 0.03 and 0, only 2 parameters going to change, the compression. So I know it's going to be division of that only. So that's why I can give the question answer in very simple form. Okay. So let's go back to something which is highly important. And that is basically the spring equivalency of the rod, which we already completed, but you know, for understanding, what is the equivalency of a rod and spring, so that I can teach you the concept of, you know, rod and the spring by relating rod as a spring. Okay. So we already completed this part, but still, if any rod is there, please try to understand, and if you apply a force on that rod, it get extended by some value x, by some value of x. Okay, please try to understand. If rod is having length L, okay, and if you apply a force on the rod F, this rod is having area of cross section A, then it get extended by some deflection, okay, which is x, or you can say delta L. Delta L is the change in the length, or x is the deformation of the rod, which is same. Okay, can I make it as equivalent to the spring condition when there is force is applied on the spring, and due to that the spring get extended, by value of x, and there is a spring force applied on the body which is equal to what? Kx. Can I apply this parameter? Yes. What is the use of these 2 parameters? I'll show you. In this condition, you are going to apply the concept of longitudinal stress and longitudinal strain. So can I say the stress is equal to E epsilon Young modulus. What is stress? Force per unit area. What is E? Is a property of the material. What is E? That is deformation by original length. So can I say, if I say like this is AE by L, if I remove with respect to S, I can relate with F is equal to Kx, and I can say the force on the force which is applied on the rod is basically what? Kx, and K is nothing. K is the spring equivalency of the rod. Okay, K is the spring equivalency of the rod, which is equal to area of the cross section Young modulus to the original length, which 3 properties are You can say the constant property that you know. Okay, Pakka? Very simple. Now, spring constant plays a very important role because it depends upon how much it get extended. Like if spring constant is very high, X will be very low for the same force. Simple. So here it depends upon which parameter. It depends upon the area of cross section, Young modulus, yes, and that plays a very important role. Please try to understand. So if you have like rod of same length and the same parameter, first I'll tell you what is this spring constant for the rod. For the rod, it is AE by L. So in that parameter, what happened to the A, what happened to the E, and then what happened to the L, which create changes in K. Only one thing is happening. So if you increase the A, the spring stiffness will increase, spring get stiffer, or you can say if the cross section area is bigger, it's very difficult to extend the rod. If Young modulus is very high, then again the spring constant for the rod will increase and the spring becomes stiffer. Means if the Young modulus, the property of the material, that property of the material is more, it's very difficult to get, stretch. But if the length of the rod is increased, its stiffness get decreased. So if the rod is very long, it's very easy to stretch, obviously. I told you like before initially also. Even in this case, if A and E are constant, which is majorly happening in the case of rod, then the stiffness of the rod is directly proportional to 1 by L. And this is the way you are going to understand the spring cutting concept. There is a concept of spring cutting that I taught you in the work energy part, that how the spring stiffness changes. But here I am going to teach you a lot about that from fundamental point of view. That if you have a spring, of stiffness K, and if you cut the spring into two parts, 1:1, means if you cut the spring in L by 2, can you tell me then what is the stiffness for the L by 2 part and what is the stiffness for the remaining L by 2 part? You know what happened? If the length become half, the stiffness become 2 times, inversely proportional. The stiffness become 2K. The stiffness become 2K if initially the stiffness is K. I think you studied like somewhere in the book, but this is the actual proof. If you are not changing the material of the rod, just understand, if you are not changing the material of the rod, means Young modulus, if you are not changing the dimension, the cross section dimension of the rod, just you cutting the rod, you are making the rod to be half, then it's very difficult to extend the rod, means its stiffness get 2 times. The same concept logically applied in the spring. One more thing. Okay. Spring constant equivalency. So in that there is a connection which is series and one in parallel. This is highly important. If you put spring of 2 constant in series and then you apply any force F, let's suppose this is K1 and this is K2. And if you want to understand that what happened when 2 springs are attached, can you convert into one spring conditions of some K equivalent stiffness in which the force F is applied? Yes, I can do that, but the K equivalent is 1 by K equivalent is equal to 1 by K1 plus 1 by K2. I can show you this relationship. This is like inverse in the resistance. In resistance, series resistance get added, but in stiffness it actually get decreased. Why? You need to feel. In parallel, what happened? Just see this. If there is a one spring is there, same spring of K1, another spring of K2, and you make it combine with the rod and apply the force F. If this is K1, this is K2, And if you want to convert the same relationship with one spring as a constant, this is what K equivalent. Can you do that? Yes, very simple. See, you need to feel, you need to start feeling. What is K? What is K? Sir, stiffness. If two springs are parallel, then it's very difficult to stretch the spring. If two rods are parallel, it's very difficult to extend that rod. So the K equivalent should be higher, and the K equivalent in this condition is in parallel condition is K1 plus K2. Both the stiffness will add together and you will get higher the stiffness. In the case of what series, the K equivalent is lesser than both K1, K2 divided by K1 plus K2. Lesser than K1 and K2 both. Why? Because when you take two rods, one more rod and apply the force, both rod gets stretched. Its equivalent rod gets stretched more. Means stiffness is lesser. Okay. There's a very beautiful connection in the series part. And how you are going to apply this? How you are going to apply this in the case of numericals? Okay. I show you directly the numerical. That would be like much better for you guys, and how to solve the numerical. There is a numerical in 2019, 2 rods numerical was there. All are like extremely simple. Okay, 2019 is there. Okay. Yeah, this is the numerical. It's a big numerical. Just I am going to go through one single part and I'll show you that how the numerical I am going to solve in next page. Okay. What are the parameter I am studying? In an environment, means at any temperature, there are brass and steel wires. There are two rods or wires are there of length 1 meter each. Both rods of same meter with area of cross section of 1 mm square are used, both having a same area. So the length and the area are going to be same. The wires are connected in series. You can solve through this method, you can solve by any other method, whatever the method you want, but I prefer you to be like just convert this rod into the spring concept. So they said there is a brass rod is there of same cross section area, and then there is a steel rod is there. Length for both the rods are same. Okay, so first one is brass and second one is steel. Length L1 and L2 are same, and the beautiful part is A1 and A2 are also same. Can you convert the same rod system into spring system of stiffness K? Yes sir. Okay. Let's suppose this is the K for the brass and this is K for the steel. What is K? Sir, AE by L. A1, L1, E1. K2 is what? A2, E2 by L2. Where A2, L2, A1, A1 are same. Only the material is different. That's why E1, E2 are there and they are in series, as they said. One end of the combined wire is connected to a rigid support and other end is subjected to elongation. The stores stress required to produce net elongation of 0.2 mm is what? And they are saying like the total stretch, the total X is basically 0.2 mm. can I determine the K equivalent? So that is K1 K2 divided by K1 plus K2 or not? Yes. What is K1? Sir, A1 L1 in very simple, A by L E1 into A by L E2 divided by A by L E1 plus A by L E2. Can I say A by L and one A by L is gone completely because they are common. So can I say A is how much? A is how much? 1 mm square. So can I say 10 power minus 6 divided by length is 1 meter. So I don't need to put, multiply E1 and E2. What is E1 and E2? Young modulus are given 120 and 60. 120 and 60. Both are 10 power 9. 10 power 9, 10 power 9. I need to understand one more parameter. The young modulus for steel is 120 and this is 60. This is half. So steel is having more modulus of, elasticity or Young's modulus, means you can actually, it's very difficult to stretch steel as compared to brass. That's why steel is used in many places where you don't need stretching too much. Okay. And below is E1 and E2. So 120 plus 60 is 180 into 10 power 9. So 10 power 9, 10 power 9 is gone. 180 with 60 is gone. This is 3. 3 with this gone is 40. 10 power minus 6 with gone with 10 power. So it's 10 power 3. So 10 power 3 into 40, that is the K equivalent you will get. If you have K equivalent, can you determine the total extension? Yes. Can I say K, if I apply on the spring, the force is equal to K equivalent into X or not, and you need to determine the force for the K equivalent, which is 40 into 10 power 3, to get the extension of how much? 0.2 mm. 0.2 into 10 power minus 3 minus 3 minus 3, 0.2. F will be 0.2 into 2 is like basically 8. Okay. So you'll get the force value to be what? 8. But you need area, or you need stress or force. What they are asking? Okay, they are asking the stress required to produce net elongation. Okay. So the stress is force by area. So 8 divided by area. Area is how much? Area is given as what? 1 mm square. So 10 power minus 6. So you will get 8 into 10 power 6 Newton per meter square. In mm square it is 8 mm square. So that is the value. Okay. It's a super difficult problem. I am telling you, this is one of the most difficult problem which has been asked in JEE 2019. People get like shivered. Okay. Okay. So that is a concept of spring equivalency, like how you can equivalent the spring. Now we'll come to the energy density, okay. You can say energy stored, all the parameters there. Then you will be able to solve any problem, okay. One energy stored is a very simple concept that you need to understand, and it is again coming from your basic fundamental, okay. But as you convert, as you convert the rod into spring, can I say you can determine everything now? So can you tell me one more thing? There's a one question is there, time period, that's why I'm doing it. If the spring constant you know and you put a weight of m, if you know the spring constant and if you put a mass m, can you tell me what is the time period? So 2 pi by omega, or you can say 2 pi by under root m by k or k by m. Okay, that is something you should be aware of, yeah. Okay, m by k or k by m by k, that is the basic fundamental of the time period of oscillation, okay, which is coming from spring part. So can I say if I give you the k for the rod is, sir, AE by L, and if I give these property, can you determine the k? Yes. If I tell you that what is the force which is applied on the body, force is mass into acceleration, or in this case is basically mg. So if you multiply g divided by g, so you will get the answer. So that is a time frequency thing that you need to apply, that's it, okay. Or you can put the value of k here only, so you will get 2 pi under root, k value is AE by L, so AE is here and there is a M, L is there, that's it. This is a time period for oscillation. It is something that you should be aware. If the series or parallel is there, that please determine the k equivalency, okay. That's your game. Now my purpose here is to tell you like what is the energy storage in the stretch rod. Energy stored, okay, in rod, and the same concept is applied in the spring, and we know what is the potentially stored in the spring. I know what is the potentially stored in the spring. I just want the similar feeling for rod, that's it. Can you tell me if I have the rod, okay, if I have the rod, can I convert now every rod which is having cross section area A and E is a Young modulus for the rod and length L is there, can I convert this is in spring? Yes, you can convert. So if I apply a force F is here and if I apply a force F is there, can you tell me what is the energy which is stored inside this rod? Can you tell me what is the energy stored inside the rod? Sir, very simple. The energy stored, the potential energy stored in this spring, it is half kx square from very childhood that we know. Okay, x is what? The extension in the rod due to the applying force. Okay, easy. That is kx square. Can you tell me what is for rod then? Sir, it is also half kx square. The k for the rod you need to put. That's it. K for the rod you need to put. What is the k for the rod? Sir, half. Sir, AE by L. AE by L, and there is a x square is there. Very simple. AE by L. Sir, in terms of stress and strain, I know few parameter which I am going to put it in this section. Okay. So the stress is equal to E epsilon. What is stress? So force per unit area, E Young modulus, that is x by L. Okay, that is x by L. Okay, that I know. Sir, can I feel something here? Like if I see very clearly, force by area is a stress. Okay, force by area is stress. I know that. If I see very clearly here that somehow if I multiply or somehow if I remove, like somehow if I multiply L in the above side and bottom side both, like let's suppose if I multiply L in the next line, I am going to multiply L for the U for the rod is, sir, I know half is there. Okay, now please see this part. Okay, if I take X separately, AX, okay, by L separately, AX by L separately, see there's AX by L separately. What is AX by L? I can see this AX by L is F by E. AX by L is F by E. Okay, and if I leave this X, okay, divide by L, multiply with L, and there's a E is there. Let's suppose not X, E is here. Okay, let me show you again. A by L is there. What I am going to do, please see this part. If I put one X here and one X separately, if I divide with the L, if I multiply with the L, what I am doing is this yellow part. Please see this part. If I take separately and if I see X E by L, sir, that is stress. Stress is F by A, and also it is X E by L or not? Yes. So if I see X E by L, this parameter, can I say U of the rod is half of stress? And if you see X by L, and if you see this parameter X by L, that is nothing, sir. X by L is nothing. X by L is nothing. X by L is strain. So can I say X by L is strain? The only parameter remain is area into length. Sir, can I say area into length is nothing? That is volume of the rod or not? Yes. That's a beauty part. That is the potential energy stored inside the rod when you stretch the rod. You know what is energy density? Energy, or you can say very clearly potential energy density. That is nothing. That is the potential energy of the rod divided by its volume, which is nothing, which is A into L. It is equal to half of the stress into strain inside the rod, and that is what I want to prove to you. And you can solve, you can derive this equation from the force work done equation also. Nothing. You know what is potential energy? That is the negative of the work done, or you can say F dot dx, integration of F dot dx. So if you take it, if you put F value as the value of the stress, which is Ex A by L into X, you will get the same value, exactly the same value. But why I want to do that? Because that is going to be slightly unnecessary. So this is important. This is important for you. The potential energy stored inside the body is nothing. It is basically the potential energy is nothing. It's basically the half of the stress and the strain, which is coming from half kx square only equation. That's it. So it depends upon the body parameters, nothing else. Okay. Easy. Thank you, Sai. Now we are going to draw the last point here, and then we can combine everything in one go. The stress versus strain curve. Okay. In some book there's a diagram is there, and it is drawn purely experimentally. It is a part of material science that you are going to study if you go for PhD or MTech, something like that. But we are not researcher, like I am a researcher, but for you guys, you are not researcher. So what do you need to do? You need to understand the concept and feel the concept. Okay. So that is a concept between stress and strain curve, and it's very important to understand. It is purely experimental. The setup is also, I'll show you the setup also if you want to now see the setup. Setup is like that like there's a rod is being placed. Okay. There's a rod. The one end of the rod is actually, fixed. The other end is actually pulled by using a device. Force is applied, and this is the original length. This is, cross section area A, and this material is having some fixed Young's modulus E. Okay. And they start stretching it. What they find out that for a certain amount of time, the stress is absolutely directly proportional to stress. Okay, till point A. Till point A, the stress is directly proportional to strain, and then they said A point is proportionality constant, a proportionality point. Why? Because the stress directly proportional to strain, and that is the Hooke's law. That you know. This is how the Hooke's law is derived. And then they stress for some other point also, and they find out like yes, slightly curve is there, but that's also a very important point. B is basically your elastic limit point. Elastic limit point. What do you mean by elastic limit point, and what do you mean by this point? I need to tell you each and everything, don't worry. So this A point is the point till when you'll find out that stress is directly proportional to strain. The proportionality is there. They are directly proportional. In this whole region, they find out that stress directly proportional to strain. Only in this region. After that point B, they said this is the elastic limit. What do you mean by elastic limit? That if you apply certain amount of force and reaches to this much of stress value, if you leave, it will regain shape. It will make the stress to be zero. If you just stretch it for up to a certain limit and leave, it will come back and reach to same value like spring. That is called elastic limit. That is the elasticity. This is the last point. Okay. When will you start? I am doing PYQ in every session. In my special class, PYQ classes are like almost like every 2 days or 3 days. We will sit together with tea and coffee and we start doing PYQs. That is my way to solve, PYQs. Okay. Then if there's a upper yield point, there's a lower yield point is there in material science, but I'm not going to show it here. Then it reaches to certain point, which is named as what, C. Then it actually dipped, reaches to a very high point, and then boom, break. So there's a point D and there's a point E is there. Okay, what is D point? D point famous is for, it's a point where you'll get you can say, where you will get the ultimate stress, the maximum stress this material can bear. So the D point is the ultimate point. Ultimate point. Okay. And whereas the E point is a fracture point. That's why I put a cross there. What do you mean by fracture point? When you reaches this E point, it actually get fractured. It get broke. After this point, it cannot survive. It will not give you any elongation. It get broke. That's the feeling of this part, E point. There is a C point, which is, I am putting you that this is a yield point, and it is famous in material science, but not for you too much. Okay, not for you too much. But the yield point is something in material science that from that point you can see the yielding inside the material. Like there's a the permanent deformation that you can actually see. And till that point, if you remove the stress, you can come parallelly. Basically, you will get permanent deformation, but you will get come parallelly. You know, till this deformation, till this point, till this B point, elastic limit point, the best part is this is a elastic region, which is an elastic region from O to B. Okay, OB region. This is O point, where you can actually regain your shape. You can come back to your original shape. But if you go beyond, if you apply a slightly more stress than the B point, you will enter into the plastic region. Plastic region means after that, if you remove the force, if you remove the stress also, still there will be a permanent deformation is there. Okay, there will be a permanent deformation. That's a beautiful part, and this is a part of material science, pure experimental, but I am trying to tell you like what is happening right now. Okay, beautiful parameter, and this is how you need to understand. See, now try to understand. If in this elastic region, this proportionality region, if theta is more, if this angle theta, or you can say the slope is more, what happened? Then for same deformation you need more stress, means its Young modulus is more. It is difficult to deform the shape, it is difficult to stretch the body. That's why brass is like this, steel is like this. Steel is getting more difficult to stretch the body, brass is easier to stretch. That's why brass is used in electronic industry and steel is used in, you know, electrical industry. You can select transformers, like wires, the transmission cables, because that is why having a good strength, less deformation. Excellent concepts there. But practically, if you go to the, you know, practical engineering part, when you go into the engineering part, you will remember everything and you will find out like, yes, okay, I am trying to give you the practical importance here only. D is important because it is the maximum stress that it can bear. This is in Hindi, I know this is the last cheek है ये, इस material की last cheek होती है, इतना stress bear कर सकता. But in English, this is you can say the last bearing capacity of the stress that it can bear is the D point. That is called, that's why it is called ultimate point. It is a next level point. Because less students are there from the only English background, that's why there is no batch. If there is a, like more student will come, obviously there will be a batch. Why E is called fracture? Because now the material get fractured. This material now broken. At this point, if you want to see at this point, now what happened to this material, I will show you the practical picture. That this material get break like this. This is the real condition. It get actually fracture. There's a more detailing is there, like cup and cone and this kind of detail, depending on which kind of material it is, brittle or ductile or this kind of stuff is there. But I don't think this is for you. I'm teaching for UPSC people, but not for you, obviously. But this, the beauty of this, you know, whole concept is very, very important. The same material goes there, and this is a pure, this graph is pure, you know, purely based on experimental part. I want to show you one thing also. Can you tell me what is half of sigma and epsilon? Sir, this is the area of the triangle or not? You know what is this area of the triangle? So that is called potential energy stored per volume or not? Energy density. That's why it is. That's why it came half into stress into strain, but only elastic region. The total area is also having some significance, but I am not telling you because it's too much for you then. Okay. I don't want you to get too much of depression here. Okay, let's go to some graphical problem. All problems are like full mechanics. If you apply the mechanics and then you apply your property of solid, you can solve each. Like this is the energy concept problem. The elastic potential energy stored in a steel wire of length is given, stretched through a 2 cm is 80 joule. The cross section area of the wire. Can you tell me what is this energy? Sir, half into stress into what? Strain into volume. They are not telling you the volume density, they are talking about the energy, actual energy. Volume density in joule per meter cube. So they are saying this is 80. Half. What is stress? What is stress? So the force per unit area, and this is Young's modulus. Okay, in every book there is a different symbol. For me, I am using E, capital E, which is they are saying Y, 2 into 10 power 11 Newton per meter square. This is basically steel. So they are asking about the area. The original length is given, the stretch part is given, mean the strain is given, which is 80 kilojoule. What is the cross section area? So what is stress? What is stress? Sir, force by area. What is strain? Sir, deformation by length. What is volume? Area into length. So they are asking about area. If you remove the area, then you will never get the point. And you have the potential energy. And you have deformation. You have original length. What sort of parameter that you have? Please try to understand. I have this parameter. I have this parameter. I have this parameter. Okay. This is the parameter that I have. I have Young modulus also. Okay. I have Young modulus also. So if you want to put Young modulus, like if you want to multiply or divide Young modulus anywhere, you can multiply and divide Young modulus also. Okay. So is there any impact by using Young modulus? Like I can like sort out. See, I cannot use this formula because then the A will be get cancelled out. So I have one more trick. Sir, U is half kx square. Half k is what? A by L into x square. So this formula is going to be used. Why? Because the way they given the data, they say E will be given, L will be given, deformation will be given, energy will be given, and they are asking about A. What is A? Solve it. So this experience you will get only and only when you start solving problems. If you are not solving problem, you will never experience this kind of stuff. Okay. So just use, see, every parameter is given, like SI unit I am going to put. So A is 2U, so 280, L is 20 meter by E is 2 into 10 power 11, and there is a x square. X is how much? 2 centimeter. So 2 divided by 100, 2 square means 4 divided by 100 means 10 power 4. Okay. So if you see 10 power 4 with this 10 power 11, it will become 10 power 7. These 2 will be gone, so it become 10 power 5. 4 with this 2 will be gone and make it 8 as 0. 2 into 2 is 4, something with 4 into 10 power minus 5. So you can say mm square they want, so you can say 40 into 10 power minus 6 or 40 mm square. Done. And start solving the problem also till the end, because that's your practice, not my practice. I know mathematics good. Frequency problem, everything is given, you know what you need to do whenever the frequency problem is there. Okay, time period is 2 pi by omega, which is in the case of spring m by k, and frequency, they are asking for frequency in hertz. Frequency in hertz 1 by t, so that is basically under root k by m multiplied with 1 by 2 pi. K value is how much? 1 by 2 pi. K value is how much? K is A by L into m. Wire density is given, so I need to divide with something, volume. So what I am going to do, I am going to say multiply the length. The area into length is the volume. Mass by volume is basically density. So 1 by 2 pi under root E upon density into length. Okay, now I need Young modulus, which is given to you. I need length. Length is given to you. Extension is also given to, but not needed. Okay, directly you can solve the problem. Okay, directly put the value and you will get the answer. Very simple. Frequency is 1 by 2 pi into under root k by m. Okay. Any other problem? Graphical problem. I need graphical problem. Apart from that, you can solve any problem. Nothing can. This is a graphical. As shown in the figure below, in an experiment, determine Young modulus of the wire by extending load curve equation is plotted. The curve is straight line passing through a origin makes an angle 45 degree. The slope of this angle is 45 degree for the extension and the load. Try to understand load per unit area, extension per unit length. Okay, extension is x. This is force F. The length of the wire is given. Diameter is given, Young modulus is given. They are asking what is the value of x. X means the value of, they are asking what is the value of, okay, they are asking the Young modulus value basically. So, stress is E epsilon. What is stress? Force per unit area, E. What is epsilon? X by L. They are saying that the F by X equation multiplied with L by A is equal to E. They are saying like F by X curve is given. This is F, this is X, 45 degree. So tan 45 is 1, finish. So this value is 1, done. L value is given to you. Okay, area for area, radius is given to you. Just divide, you will get E value. Finish. Problem is done. As you can see. So directly is L by A. Okay. Because F by X, this is load, this is force, this is extension X. F by X is 1. So E is directly L by A. What is the length which is given to you? 62.8 centimeters. So divide by 100. What is the area given to you? So that is diameter is given. So pi by 4 into what? D square means 4 square. 4 into 4 into 10 power minus 6. So the E will come out to be, or directly value is coming now. So very simple. Pi is 3.14. Can I say if I multiply with this 2, it will be gone? Yes. So I need to just multiply 2, divide by 2. So this 2 and 3.14 can cancel this out and make it 10. Okay, then the pi will be gone. This 4 will be gone. This 4 will be gone with this 2, and this 100 will be gone with this 10. Mix with this 10 power minus 5, gone up 0.5 into 10 power 5, and they are asking in 10 power 4. So must multiply, you will get the value of x directly, the 5. Okay. Any other graphical problem? Graphical. Yeah, this is the graphical problem. This is extension by load and this is the wire length. So this is length, this is x by L, load. So what is stress? Stress is E epsilon. What is stress? Force per unit area. What is epsilon? X by L. So what is this given? X by L. Sorry, x by force, and this is wire length. So can I say this is a wire length also. So can I say 1 by AE is basically what? X by F and divided by the length. You know what is x by F? This is y and this wire length is L. So can I say this is basically your, if I take this as a y axis, if I take this as a x axis, so this parameter will be given to you, and this is 1.1, this is a kind of straight line, okay, 45 degree. The value is, you know the value, this value you know every point, this is 1 kind of, and they are asking the area. For area they must be given the area, and they are asking Young modulus, which is very easy now. Again the similar problem. Yeah, this is the last topic, done. So directly you can use this part, okay. Slope is, you know that slope, you can determine the slope. Any other? Oh, okay, graphical problem. I like graphical problem. Stress and strain given in the reverse direction. This is the stress, this is the strain. Because they know you have all the idea of stress is here and strain is there, but it doesn't matter to you. The elastic behavior of a material for linear stress and strain is shown in the figure below. The energy density for a linear strain of 5 × 10 power 5 is kilojoule per meter cube. Assume that the material is elastic up to the limit of 5. See where the point of 5 into, so this is the point, na? Some point is there 5, and for stress versus strain, this is the area, half of sigma into epsilon. Finish. If you are putting the, if you are saying the strain is 5 × 10 power minus 4, minus 4, this is limits in minus 4, this is given wrong, okay, minus 4. Then can you tell me what is the stress value if 20, 40, 60, 80 is there? Next is must be what? 100 into half, done. Okay, finish. 25, same, like this is divide, this become what? 50 into 5 is 250 or 2.5 × 10 power minus 2, and they are asking in value, and this value is given in what? Like strain is given in like dimensionless, this is Newton per meter square. Okay, so they are asking kilojoule, okay, that's why, nothing else. So the whole concept is same, bro, nothing difficult. Super easy problem, super easy problem. Okay, stress into strain or strain square into y, whatever it is you want to put, okay, directly you can put. Any other graphical problem? I don't think so, like all the graphical problem is like, and this is advanced problem after this, okay, 2019, 2010, whatever the problems are, like super tough advanced problem. So if you start solving those problems, you will be like top level, don't worry about it, okay. For remaining all the problem, please come to my special classes, very very important for you guys to come, okay. Okay, done. So let's meet in next lecture. Bye bye, take care.